the need for new forms of energy is really the fuel of all this development, you know.
In clean chemistry, the biggest strength we have developed is now there is a strong group of collaborating people across Europe dedicated in working on this technology.
We managed to produce nanopowders able to give excess heat on nickel in hydrogen. And these nanopowders are manufactured in a very simple way.
So with using nanoparticles of materials, you have a lot of surface, little volume, almost only surfaces. As I told you, the experiment is happening at the surface. Let's have only surfaces. So that's why we go to nanoparticles. And because of this collaboration, we could produce these nanomaterials.
My colleagues Jean-Paul, Biberian, Mathieu, Valat, which are members of the clean chemistry process, are involved in the process on how to transform this precursor, which more or less is a sponge of water, because it contains a lot of water since it's been performed in water. So it's an hydrated mineral, and also it's a carbonated minerals, which makes the layer of the product. And this starting material has to be decomposed, let's say torrefied, to become an active material for LNR purposes.
I was lucky enough to know Christophe Roux, who works in Toulouse at the CNRS. He's a chemist. He found a paper in which, with hydrotalcite, you could produce nanoparticles.
Well, when I saw one paper, I remember very clearly one paper, it was a review paper, and I saw a picture showing that hydrotalcites could lead to nickel nanoparticles on alumina. And when I saw this picture, I said, we have to try that. And I did it. It worked perfectly well, like I did today. So it's very easy synthesis. And this is the one that I sent to Jean-Paul.
He made a product based on nickel copper with aluminum matrix. So very similar to what Takahashi was doing, but instead of zirconium oxide as a matrix, we're using aluminum oxide as a matrix. So very, very similar. But the technology is extremely simple.
You know, for the memory, Jean-Paul received the first sample of hydrotalcite 2 days before the kick-off meeting of the clean chemistry process. This is right.
So he gave me this powder, and I didn't know if it would work or not. But as he said, this powder produces nanoparticles of nickel, and we know that nanoparticles are effective. So I put it in my calorimeter, and at low temperature, nothing was happening. I went to higher temperatures, and above 700 degrees C or maybe 800 degrees C, something happened. And there was excess heat only above certain temperatures. This is the calorimeter. Heat flow calorimetry. It's very precise because I can go to 1000 centigrade with a precision of between 100 and 200 milliwatts. So that's very important. This is a quartz tube. This is 2 centimeter diameter, 9 centimeter length. In that tube, I put the powder, the green powder. Yeah. This green powder goes inside. And then I realized that by loading and deloading, that was increasing the amount of excess heat. Like so far we have about, the best experiment was more than 10 watts with maybe 20 grams of powder, something like that.
Now the platform that we have, which is the hydrotalcite, we have a non-sintering powder. So we have properties that allow us to go to higher temperature, hence to sustain a reaction into a configuration that will be producing a lot of energy, useful energy.
So we put together a procedure to produce excess heat.
I am Robert Michel. I am the founder of this company, Vegatech. We are based on the microelectronic technopole of Roux, south of France, near Aix-en-Provence. Why we are here? Because we are member of the Clean Chemie Consortium, and we developed several calorimeters, microcalorimeters, to check the LENR effect.
The reactor is here, the same as in my case. It's here, inside this. The same as mine, but still all closed so you don't see the inside of the water. There's water inside to keep temperature at constant temperature. And this is the vacuum pump to pump the cell because it is under vacuum. And there's another pump here to pump the gases, to put gas inside, remove the gas, we use this pump now. So we have two pumps. And as you can see, it's much cleaner than mine.
We suppose that the effect is proportional to the mass, the quantity of the nanopowder. So in order to see more excess heat, we have to use a more amount of nanopowder. The first calorimeter, we can put in the first calorimeter 150 grams. And on the second, the bigger calorimeter, we can put 800 grams. We measure the power in, the power out, the thermocouple inside the powder. Then also the outside the vacuum chamber, we have the isolation system, and with 280 thermocouple. The scale-up is not so easy. We have to understand what are the mechanisms inside the nanopowder.
Now the only challenge we have is to amplify. I mean, I can get a few watts, up to 10 watts in the last experiments. But if you want to have 1 kilowatt, then you have larger quantities of material. But you have cooked, you know how to cook. You can cook rice for one person, that's one thing. If you want to cook for 1,000 people, it's more difficult. It's the same technique, but you'd have to change the size of your equipment. You see, the powder has to be prepared. So you need some preparation inside the reactor. And this preparation is more complicated when you have more mass. So that makes our life a little bit more difficult. So that means we do experiments, try to make it work, and then we have to analyze the powder to see if the powder is in good condition. And that's a challenge because if you go from 10 or 20 grams to 800 grams, it's a big step. Maybe the step is too big, I don't know. But we're taking our chances.
Because we are loading the nanopowder with hydrogen. And so we don't know exactly if the hydrogen is a big amount of powder is diffused, going inside properly.
Just like water plants, if you want to water plants, if you have only one plant, it's easy to put the water there. But you have many, how to make sure it goes everywhere to all the plants, If it doesn't go, the plant will die, it will not do any good. So, it's a learning curve. It takes time to learn. Once we find a solution, it will be simple. But first you have to find how to do it.
So the system are working. The two systems are working very well now. The question is maybe we have to look for better nanopowder. I don't know. We have to check other material.
So my name is Christophe Roux, and I am a member of the Clean Chemie European project. So I am a researcher for the CNRS here in Toulouse. CNRS is Centre National de la Recherche Scientifique, so I work here for the CNRS in the geological lab, which is the JET in Toulouse. And in this special part of research involved in the Clean Chemie project, I am preparing hydrotalcites, which are mixed metal oxides and which are lamellar minerals, lamellar precursors.
This naturally occurring phenomenon of the type production starts from a solution in water where we just add salt that will be dissolved in that water. Then there is a kicker to this reaction, which is very important because it will precipitate the salts into a lamellar structuration.
So you have layers, monolayer of alumina oxide, a layer of water, a layer of nickel oxide, a new layer of water, a new layer of aluminium oxide, and so forth. So this is interlayer at the molecular level.
So these minerals, this powder, are green, so you can see that, and non-magnetic. This is a magnet, so you can see it's non-magnetic.
The green color comes from the nickel. It will indicate there is nickel in it.
If there's nickel, and you know nickel is magnetic, but you put a magnet here, nothing happens, you know.
No,
the same powder, after use
in hydrogen
is magnetic.
And after treatments, this green mineral become this black powder. And this is the mineral that is involved for LNR purposes. And you can see that now the mineral now becomes magnetic because the nickel, which is nickel cations in this powder, are reduced as nickel metal nanoparticles. Okay, how to prepare this? So it is very easy. So you have to mix just two solutions, and it is the beauty of the synthesis of hydrotalcites. So nature makes all the stuff. So you have just to mix chlorides or nitrates of the elements you want to build the hydrotalcite. So it's, for example, in this case, it's nickel, copper, and aluminum. So in the right proportions, and you just have to mix this with a base which contains the carbonate and sodium hydroxide. So it's a very easy and very fast process. As I can show you, the hydrotalcite is done now. So now you have performed, it's done. So here you have hydrotalcite in almost 100% yield. Of course, if you let the reaction proceed, if there is an aging time, the hydrotalcite will be much more crystallized. But even here, you have hydrotalcite.
Then we remove the water and we obtain what is look like a colored salt, talc, like you would buy in for baby powder. And by being born into water, it still has a lot of water in it. So if we want to do something, we first have to clean it up.
If you analyze the water which is obtained by this process, the water contains only 40 ppb of nickel parts per billion. So that means almost nothing. So that means that in this process, all the nickel, all the copper, all the elements have been precipitated on hydrotalcite. You can almost even drink the water after the synthesis because it contains almost no nickel in the process.
You have to do some treatment to the material to make it active. So that's the difficulty. Sometimes if you have oxygen, I mean the nickel is not like gold. Nickel get oxidized. But if you have oxide layers on top of nickel, it doesn't work. So you have to remove the oxygen first. If you don't do that, it won't work. We have the proof because we did the analysis. He did the X-ray analysis showing that the sample I sent him was nickel without oxide. Very
the first one.
The first one was a good one.
Oh yeah.
You know, the luck of the beginner. You know?
Yeah.
Next step is to make sure it works, produces a lot of heat, and then we will look for better powders that will have a better yield.
This powder is nanostructured hydrotalcites. So you can play after with the ratios of the elements you put in it.
We can design the amount of amorphous structure to the amount of metallic active sites. And by being able to design the powder the way we want, we can design the nuclear active environment that suit the reaction to occur.
So far we're using nickel and copper. We have tried pure nickel, which gives more or less good results. We have tried other materials. So we're trying different alloys and see which one is the best.
I'm trying to conform and to improve the parameter of that powder to enhance the nuclear active environment. I'm designing a nuclear active environment to the nanoscale.
We know now much more than we knew 4 years ago. We know how these powders react. We know that the hydrogen must go in and out. We know how important it is to remove all the oxygen, for example, in this powder. It's not a surprise, but we had to manage how to do it.
Biggest benefit of this Horizon 2020 type framework project is that it helps to fund collaborative projects among all the Europeans, and even broader now because it's been extended.
Some other laboratories in Italy, in Belgium and Sweden are working with the same material now because we have shown it works. So they're trying to repeat the experiment.
We are quite happy to have reproduced excess heat effects with the powder, nanopowders we are using.
I think one of the most significant replication is happening now in Italy, where you have this simply hot tube heated by an industrially designed heater. It's very inexpensive, it's very simple to run it, and it seems to be showing great results.
Collaboration between people doing chemistry, me doing calorimetry, some other people being capable of measuring radiations.
How collaboration on the sample preparation, the experimental improvements, on the exchanging samples, techniques, measurement systems, instrumentation, nuclear measurements. All these helps us into having a valid scientific set of data to make our case.
More and more people say that nickel energy is working. Look at what is happening in Japan. Look at the development in USA. At least we should try to find out if this is working as some say or not.
We just opened a new door into cold fusion, something very inexpensive that I showed you, which is very inexpensive material, and we can make nanoparticles.
Soon we will be able to design and produce cold fusion materials with an expected production of energy, with basically all the engineers that will come after.
Because we are very close to a solution. I mean, a practical solution that will produce a lot of heat. Because we have the right powder, we just need to amplify the phenomenon, which is not difficult because we have everything to succeed. But again, it's just like cooking rice. I mean, cooking 1 ton of rice is not like cooking 100 grams of rice. So we are there. As soon as we have solved this problem, maybe by the end of the year, I don't know, maybe later, then we can go into applications.
What I say is that it's one of the sexiest field of physics to study right now because of this multi-physics aspect and because we are getting there.